go. Here we go, here we go. Here we go, here we go. Here we go, here we go, here we go, here we go, here we go. Here we go. Here we go. Here we go, here we go, here we go, here we go. Here we go. Here we go. Here we go, here we go, here we go, here we go.
Hello everyone, and welcome to another episode of Containers from the Couch. Today we've got an exciting episode. We're going to be talking about how you can run Spark workloads on Amazon EKS or Kubernetes in general. Specifically, we're going to go dive into AI and ML workloads as well, showcasing how using this open source project, which my guests today are closely collaborating with, called Data on EKS, DoEKS. We're going to show exactly how you can use that project to quickly get started with running highly intensive data processing workloads on Kubernetes. So if Spark or Kubernetes, if either of those terms seems a little alien to you, don't worry. Our experts today are going to walk you through it end to end. But very quickly, I'll tell you that Spark allows you to run computing workloads in a highly distributed way. And of course, Kubernetes is a container orchestration system. A critical part of Spark is this compute manager of where Spark workloads run. And Kubernetes slots into that perfectly. And so today I want to introduce my guests, Alex Lyons and Vara Bonthu. Alex, I want to start with you. Tell us a little bit about what you do at AWS and what brought you into the Spark and Data on EKS project.
Yeah, absolutely. So my name's Alex. I work on business development and go-to-market for Amazon EKS, and specifically on this Data on EKS project. And what Data on EKS is it's an open source project to help customers modernize their data workloads with Amazon EKS. Now, I came to work on Kubernetes. I've been on the containers team for about 3 years, and Kubernetes has been growing for more than 3 years. But I remember seeing a stat from I think it was the 2021 CNCF survey, 96% of organizations using or evaluating Kubernetes, right? So it's big, getting bigger, getting super popular. And one of the things that we've realized in the past couple years is that data processing and data workloads like ML and stream processing and things of that nature have been getting more traction in the Kubernetes space. Now Spark is a distributed data processing framework. What does that mean? You have terabytes and terabytes of data. As an organization, you need to process that to use it for things like machine learning, right? You need structured data. So Spark can distribute that over multiple nodes, multiple partitions, and process that all the more faster. Distributed, that's what Kubernetes does, right? It's an orchestrator. So these two things marry up really well when you can start to translate Kubernetes concepts into things for these different data tools. And we'll get more into the weeds of that later. But yeah, that's kind of how I find myself here and how we all find ourselves here talking about data workloads landing on Kubernetes.
Excellent. And I love that notion of Spark and Kubernetes being a really solid marriage, because it does make sense, the distributed nature of Spark workloads being able to benefit from parallel processing, and how Kubernetes, especially when running in the cloud, that burstable ability to get resources on demand, run the workloads, and then scale back down also ends up helping you save costs in addition to being highly efficient. So really great stuff there. Vara, I want to pass it to you next. Vara is going to be our expert SME demoer today. Don't get me wrong, Alex is also our expert, but Vara is going to be driving the demo from his laptop today. Vara, tell us a little bit about yourself and show us a little sneak peek as to what you're going to be demoing for us today.
Yeah, sure. Thanks, Sai. Thanks, Alex. Hi, everyone. My name is Vara Bonthu. I'm a principal open source solution architect, mainly working with the strategic accounts within AWS. I'm also technical lead for Data on EKS, and I'm very excited about introducing all of you how you can actually run data and ML workloads on EKS, and that's where the Data on EKS comes into. For today, we're going to talk about how you can actually run Spark workloads against a synthetic data warehouse data using TPCTS benchmark, right? So on Amazon EKS. The purpose of this TPC-DS benchmark is mainly to measure the performance and the scalability of the data processing systems like Spark in this case. So let me show you quickly how the benchmark runs and what we are going to do.
Excellent. So just
this,
so we're clear, just really quickly, Vara, for our guests here, we're showing how we can run a benchmarking, a benchmark rather on a Kubernetes cluster, which demonstrates a sample Spark workload, right?
yes, that's correct. So typically the benchmark is used to measure the performance of the Spark, but it also helpful for the customers who wanted to identify which type of compute and storage is better suitable for their type of workload. So this is just an example, and what you see here is the benchmark which I'm already running now.
Vara, just sorry to interrupt. Could you make this a little bigger? And it looks like you're looking at a cube lens dashboard for a Kubernetes cluster. If we can make that a little bigger, I think what it looks like we're looking at the pods in a particular workload.
Thanks.
Okay.
And just zooming in a little bit is how does it look? Right. Okay.
Yeah,
so this,
better.
what you see here, the benchmark, the pods are running, the executors, there are like nearly 50 pods, 47 pods. And most interestingly, because you all wanted to see how the Spark job is performing, and this is the live TPC-DS benchmark with the Spark history server. And we're going to go into the details as a part of the demo, but that's what I wanted to go through. And when we have more time, and I'm also planning to show you the EMR and EKS, which are managed service, comparing with the open source Spark and how you can run two different jobs.
So the scale of this thing is mind-boggling to me. If you switch back to that Cube Lens dashboard, each one of those line items is essentially pulling over 7 gigs of memory. And when it was running at full speed, I think I saw it was each using 3 or 4 cores. Now I see we're at a fraction of that. Maybe it's doing a more memory-intensive part of the benchmark rather than CPU-intensive. But still, I want folks to realize like the scale of this. And it's not all happening on a single machine. You're not just, if you were to run the Spark workload on your local machine, maybe it's parallelizing a few different threads, but not to this scale, right? What we see here is, wow, that's quite a few nodes that's running this workload.
That's correct. So we have C5D instances. We are running a small set of benchmark, but if you want to go for 10 terabytes, and you might need more instances to see the results. But yeah, this is just to showcase how you can run that, but the actual workloads are pretty much similar to this, and we can go through what are the best practices as a part of the demo.
Excellent. Okay, so with the promise that Vara is going to show us exactly how he set all of this that he's showing us later, I want to jump back really quickly here to Alex, because I think it's critical that we talk a bit about the data on EKS project, DoEKS, which I love that abbreviation, by the way. Alex, tell us a little bit about DoEKS and how it's helping our customers do AI, ML, and more on EKS.
Yeah, absolutely. So data on EKS, again, it's an open source project, and we have what we're referring to as blueprints. So what's in a blueprint? A blueprint is a set of sample code that is built to run one of these workloads that we have targeted. So Spark is the one that we're looking at today. We also have machine learning, we have stream processing, really the core elements of data platforms and data applications. But we have sample code that helps a customer or a user, right? Anyone can go out and use this, spin up the AWS resources with the right configurations and install the right open source tools and do all of that with our AWS practices built in. Along with that, we have things like reference architectures. So if you're going to go and run this sample code, you can have a visualization of like, what is it that I've just spun up and how would I use it, right? We're running these benchmarks, or we're training a machine learning model, like not just spin it up, but how do I kick the tires, right? Make sure this thing's actually working.
Exactly. And so we know that we want to run a Spark workload like Vara showed us. And we know that Spark has been around for a while. In the past, people were running Spark workloads on Hadoop clusters. So essentially access to having multiple machines to be able to effectively run these workloads. So we know, you mentioned Kubernetes is getting more and more popular. and the Spark community has definitely grown a liking to Kubernetes as a whole. So let's talk about that a little bit. Why Spark on Kubernetes in the first place?
Yeah, well, customers are turning to Kubernetes to manage more and more of their kind of technical estate, right? So sometimes the term Kubernetes standardization is thrown out there. And what that really means is, hey, an organization is now comfortable using Kubernetes, right? You can use one tool chain across the organization and start to bring more and more applications on there. So that's where we start to see some of these data applications moving on. And then why Spark in particular? Well, we talked about that distributed nature, right? Kubernetes is an orchestrator, great at orchestrating different microservices, and Spark by nature is distributed processing. So you start to see these these capabilities of orchestration and scheduling really having a nice fit together alongside the overall movement of, people are wanting to put more and more of their workloads onto Kubernetes.
So it might be a good time now to just quickly recap, where Kubernetes fits into this picture, and maybe a history of data and Kubernetes and how we got here today.
Yeah, absolutely. Is there are we walking through the slide, or is this okay? Cool.
Let's do it.
Let's do it. So Kubernetes was launched back in 2015 as an orchestrator for stateless microservices. But it's continued to evolve to meet the needs of its users and the community over time. And specifically, there were two features, and we saw really kind of jumpstart this development of data tools, making themselves accessible or compatible really with Kubernetes. That was a CSI driver. So now you can start to manage your storage options, which brings in that stateful element that we need here. And then also custom resource definitions, or CRDs, which let you manage non-Kubernetes resources with the Kubernetes control plane and extend those orchestration capabilities to other applications. At that point, we saw the response from the data community where these data tools said, hey, this could be a good fit for us, right? This could be a good way to manage these applications. And we saw operators built for Kafka, for Spark, for these things that we see on the screen. We saw a similar kind of wave in 2019 when GPU support was released. That's obviously very important for machine learning, right? And then the machine learning community responds in turn with releasing open source tools like Kubeflow, which is an ML operations tool specifically for Kubernetes. It's Kubernetes native. And then also, machine learning tools like Ray from the folks at Anyscale, Jupyter Hub, which is the notebook, shared notebook application, start to release support for Kubernetes. And then we continue to see this type of evolution with more and more tools being built. It's like Unicorn's another example, which Var is going to talk about in the blueprint, which is a Kubernetes specific batch scheduler. So we expect that this type of progression is going to continue, especially as data tools and Kubernetes are evolving side by side.
Makes sense. And of course, on the left side here, we see more of the traditional solutions here, which, 10 years ago, you wouldn't have even really connected these to AI and ML use cases. But underneath the covers, when you look at something like Spark and data processing nature of it and the type of data it's so effective at processing, it just made sense for AI ML workloads to leverage that same distributed computing platform that Spark is. And of course, on the right side, we see some of the more Kubernetes native solutions that were created in the space. But okay, so far, so good. I think it's good to have a history of how we got to where we are today. But customers still have a gap today, right? And they need help in learning how to run these things. So where do the challenges lie?
Yeah, so in working with customers, we recognize that there were some core challenges to running these types of workloads on Kubernetes. So the first one on that slide, scaling. These are data intensive workloads. There's memory attached to each of these pods, and they need to scale up and scale back down very rapidly, and sometimes to over 1,000 nodes. If you're talking about one of these Spark workloads and you're doing all of the data processing for a very large organization, it's got to scale up and then back down pretty rapidly. So your EKS cluster is going to need some specific configurations to be able to handle that. Another example is the network configurations. If you think about something like machine learning training, where you're going to distribute that training over multiple nodes, there needs to be a really high level of interconnectivity between those pods so that you can get that training done and they can share the information that they need back and forth with each other. Another one that we saw come up in nearly all of the customer situations is failover. If you need to build a highly available architecture for stateful applications, it just has a whole additional set of considerations that you need to bake into building that architecture.
Excellent. And so I know we started our conversation today talking a little bit about data on EKS. Of course, Alex and Bara both being leaders in the space, working with the project and the community. Tell us where data on EKS fits into the puzzle here.
Yeah, so data on EKS is, well, I'm going to take a step back. This visual is a depiction of what it is our customers that are running on Kubernetes and specifically EKS are trying to piece together when they're building data platforms. So there's different stages, right? You need to ingest the data, you need to process it. Sometimes you need real-time processing. There's machine learning involved. There's all these different pieces of the puzzle. And within each of those, there's AWS managed services that can help. There's also a number of open source tools that can help. What Data on EKS is doing is trying to curate the list of here are the open source tools that we see as most prevalent and most effective, and also the AWS services that can help. We're going to provide the option to go forward with both and allow customers to choose from a curated list. And we're also, even though we're giving those options, there's an opinionated slant to it because we're saying these are the ones that we see are most effective. We're also building in here's how we would deploy it based on our best practices. So there's a balance between being opinionated, but then also giving customers the choice to run things the way that they see best for themselves.
That makes sense. And I see on Bara's screen, he's pulled up data on EKS. So I'll switch to his screen really quickly here. So clearly, this is an open source project. We've created this in the community. There's a GitHub project that goes with the Git docs that we see here. Tell us a little bit about why we decided to do it this way, to build it out in the community rather than maybe making a service or something similar to run these types of use cases.
Yeah, by building it in the open source, we're making it available to everyone, right? We want to make it as available as possible, as opposed to, if this is a service, then we've got to go and reach out to customers. And, maybe if there's a student who's doing this in a test environment, they may not have that visibility, right? So this is our attempt to just make it as visible and as usable as possible. Really try to spread this information as broadly as we can and get it in as many hands as we can.
Right. At the end of the day, I think it's partly about operationalizing a lot of these open source tools, bringing them together and making them a pattern that our customers and our users can reuse. Tell us a little bit about how users can expect to maybe use data on EKS to run something in production. Would you use production ready as a term, or is it more of a starting place?
Yeah, that's a good question. So, production for me, production for you, if we're at different companies, is going to look different for both of us, right? So we don't use the term production ready because what you take out of our repository isn't built specifically for your environment. Now, that said, we're building these so that they're architected to scale. So these are built to get to a production scale, but they're not necessarily production ready where you can take this and plug it right into your environment. So the way that someone would typically use this and the way that we see our customers using this is they can either take it and deploy it in a POC environment and use the test that we have in the blueprint there. And then when it's time to get to production, they're typically cloning it and then making adjustments so that it fits, fits their requirements. And then it's kind of in their portfolio of infrastructure as code or IAC templates. So we're helping, add by templatizing it, they can take it and make it part of their estate.
That makes sense. At the end of the day, a customer might say, hey, I need to run a data processing workload on Kubernetes. And you can very easily say, oh yeah, there's a Spark operator out there. Go ahead, have fun. But very quickly, being solutions architects, I'm sure both of you work with customers that say, okay, I've done that, but how do I get observability, logging? How do I get monitoring? How do I scale this up? How can I ensure that my compute scales up when I need it and back down when I don't need it? So a lot of considerations in the space. And so I think that's where the Blueprints project, Blueprints for Terraform, which allows you to run a number of things in addition to EKS using things like Terraform, or we also have Blueprints for CDK and Crossplane as well. So really, this is a spiritual successor for AI ML use cases, leveraging that same blueprint technology that we've put out there with EKS blueprints, but for these specific use cases. Okay, so we have an action-packed demo for you. We want to make sure we have enough time to get into that. Vara showed us a sneak peek of running multiple parallel workloads in Kubernetes at the same time, each utilizing quite a bit of compute. But how do we get there? How do we run a distributed, scaled Spark workload on Kubernetes? Well, Vara, I'm going to hand it off to you now. Tell us how you get started from step one.
Yeah, sure. Thanks, Sai. Right. So, like we talked about, we've seen how you can actually run benchmarks. We've seen the actual results here. But let's see how we can get to this, right? So there are two ways that you can run Spark on Kubernetes on Amazon EKS today. One is open source Spark, which is using Spark operator with Unicorn. That is what the example that we are going to use in today's demo. So let's get to it. If you want to deploy this blueprint and get familiarized with this blueprint, I would say start with this documentation, narrow down to data analytics on EKS, and click on the Spark operator with the Unicorn. So this documentation will give you pretty much everything that is required for you to understand what we are deploying as a part of this blueprint and why we are deploying, what is the Unicorn is about, and how to leverage various type of storages for running the workloads like NVMe SSDs, EBS volumes, and even FSX for Lustre and so on. And then talks about Spark operator and how it is different from other managed services like EMR and EKS. So we also have a bunch of examples here to show how you can run Spark examples with Karpenter and even Cluster Killer and managed node groups. And finally here that you see a TPCTS benchmark, that's the example that we are going to run today. So let me go through how you can actually run this TPCTS benchmark. To do that, you need to install everything. So let's start with the deploying the solution, right? So let's click on this deploying the solution. If you see, it's pretty straightforward. We made it, these blueprints written in Terraform in this case, and all that you need is the prerequisites to install AWS CLI, kubectl, and Terraform. You can run it from Cloud9 IDE or your Mac or whatever you prefer. And the first step is just cloning the repo. So this has got a lot of blueprints. You can just clone the repo and then change the directory to Spark operator. In this case, it's under Analytics, Terraform, Spark operator. And change the permissions. And there's a script called install.sh. We automated to run Terraform using targets so that you can actually deploy the Terraform in a step-by-step. So let's go and see what install.sh does and see what it actually deploys, right? So let me jump onto the code.
So realistically, to get started with this, you don't need anything. You don't even need a Kubernetes cluster. Okay, I shouldn't say you don't need anything. You need a laptop, you need an AWS account, you need the billing hooked up. But once you have that, starting from scratch, this should take care of spinning up not only the Kubernetes cluster, but installing all the components that I need within the cluster as well, which I'm sure you're about to show us.
Exactly, you're right. So now I clone the repo. Once you clone the repo, you see all the directories. So if you expand analytics, under analytics, you have CDK and Terraform. But in this case, we are using Terraform here. Under Terraform, we are looking at deploying Spark K8 operator. This is an open source blueprint, which also uses other schedulers like Unicorn and so on, right? So let's go to the install.sh. Under this, you have two scripts, install and clean up, mainly for installing and cleaning up, like a utility to help you install everything. So what it does is the infrastructure deploys VPC, EKS, and bunch of add-ons, right? And that makes it the whole end-to-end deployment for your Spark K8 operator with observability, logging, and so on. So we are using this install.sh script to apply these module at using targets. Like first we deploy VPC, and then we deploy EKS, and we deploy all other resources. It's just a simple shell script to make it to avoid any race conditions while deploying. You can even run Terraform apply, auto approve, and just on that. But sometimes you get into issues where, hey, EKS is not created, and the add-ons failed, and so on. So just to avoid that, we built this. So let's look at what this is deploying, right? So we built all the best practices within these blueprints. So starting with VPC to deploy Spark AH operator, and especially when you're running a large, scale workloads and maybe 50,000 pods with 1,000 plus nodes, you really need to avoid these IP exhaustion issues, right? So for the VPC, we introduce this secondary CIDR block as a standard when you are deploying your VPCs. So that will give you 65K range, like 65K ports and a single AZ to run your workloads. So this is a simple VPC that you deploy. And you also have other options of deploying endpoints and VPC endpoints, which can be enabled and disabled. And once the VPC is deployed, let's get to the main dot here. And this is where we deploy EKS cluster. So in this module, so just moving there. So this is the main bit. We are installing EKS cluster, the latest version, which is whatever the version 1.27 or 1.26, whichever you prefer. So once you deploy EKS cluster, and we are deploying 3 key node groups. Let's get into each one. So core node group. This is another best practice that we ask customers to look at, is creating a core node group. Core node group is basically a system node group to place all your system critical parts. That can be, a core DNS and the VPC CNI, that's daemon set. Any deployment, system critical deployments can be placed on core node group, like observability, and even Karpenter and so on. So all of these will land in core node group. And how you do it
very quickly. Sorry to interrupt. We did get a question here about, if you're just not really and maybe an expert in Terraform, well, what is the percentage of Terraform knowledge one would have when using this example? And I guess another way to think about this is, say you're coming from the world of Spark. How much of this do you really need to be an expert in?
That's a good question. I normally talk about, you need a good knowledge of Terraform. The reason being, when we talk about running data workloads on Kubernetes, it is a 2 personas. So one persona is a DevOps who has a good knowledge on Terraform and other DevOps skills like Kubernetes and so on. And the second persona who only cares about writing your, PySpark jobs or, data related jobs, and then you just submit it. The way we design in such a way that, the 2 teams, one takes care of Kubernetes and, the Terraform bits, another team mainly focusing on the data processing and submitting the jobs to Kubernetes.
But is it fair to say that if someone wanted to just run this example, they could just run the install.sh script and have a cluster with the Spark operator ready to go without really modifying most of this?
Exactly. So I think once you hit some sort of issues, that's when you started to think, where do I have to go and debug? But mostly, yes, you can simply go and run install.sh, everything comes up, and then you can reach out to us if you hit any issues, we can help you out. So yeah, sounds basic good. Knowledge will be sufficient to go ahead.
And I think I took you off your track here. So just to recap, what we're doing is we're deploying a Spark operator on Kubernetes to run the TCP/DS benchmark, which is just a way for us to verify a number of compute related tasks that Spark will do on Kubernetes. You're walking through the compute where the Spark components themselves run, right? That core managed group. And I know that this is a question for a lot of folks, is how do you split up all of the different components of Spark? How do you decide the best practice of where each one of those components run? And so clearly you said, okay, let's have one node group just for the core components of Spark. Okay,
that's right.
What else?
So once you create core node group, now let's talk about the actual workload. So you always have to separate your data workloads to be run on a dedicated node groups or a dedicated provisioners using Karpenter. So in this case, we are two node groups. One is Spark on demand, which is R5D in this case, but you can choose C5D as well. And we also have Spot node group, which is mainly to place executors. You see the difference? One is an on-demand, where the reason we are placing all the Spark drivers on on-demand so that driver won't be crashed when there is an interruption to Spot. And to optimize the cost, we are placing all the executors onto Spot node group, and where you can use mix of instances where you want to place your workloads. So if you see here, this is one approach if you are leveraging cluster autoscaler and managed node groups. And the way you place the workloads is using labels and taints. You can say your driver should place on using specific label and tolerations, and the same for Spark node groups using labels and taints. So
okay,
let's.
So Vara, for your first example, we're doing managed node groups, cluster autoscaler, standard. I know in the next example, you're going to show the Karpenter approach, but let's save that for now. We did get a question in chat. So we've talked about the compute, the types of nodes that are being used. And I think this question is spot on with when it's come up. What are the primary challenges with running data persistent workloads in Kubernetes? And how do you work around the limitations of attaching PVCs? So I saw in that comment that R5D compute instance you're using comes with NVMe SSDs attached. I saw that in one of your comments there. So I'm guessing that's a really straightforward way of making sure that your instances have, local storage attached. You just get instances with the instances kind of already attached, and then you just tell Kubernetes mount this storage device at / whatever on my node, right?
Exactly. So let's get, I would like to talk about the storage, and this is really interesting topic that you see here. Like I said, we are using R5D instances. The D instances always comes with NVMe SSD. For Spark workloads, if you want a high performance, low latency from the Spark workloads, you can leverage NVMe SSD disks. So let me show you, visualize this, how it looks, so that it makes sense better. So if you're looking for a critical report, or if you're looking for a high performance Spark workload, so the storage is really important. The way you choose the storage with the compute is really important. So here you see I have EKS cluster, I have a code node group, which is with M5X large, and my on-demand node, which is R5D instances, and my Spot node group with R5D instances. I also made a block here, NVMe SSD instance storage, which is kind of attached to this EC2 instance. As you see, there are no other network involved here. The NVMe SSD is basically a storage that comes with EC2 instance, which means if you pull the data from S3 for data processing, the data is stored within the same compute within the SSD, so that you have better performance when it comes to shuffling the data across the nodes and also interacting with the data. So, but the alternative option is leveraging EBS volumes, right? So you can also use EBS volume, which is detached from the EC2 instance, but you can have there is a network latency between EC2 instance. The type of instance that you choose, the speed of the network varies based on the type of instance, and that talks EBS volume.
Excellent.
So in this case,
Vara, you're chiming in with another answer to a question that's come in at the perfect time here. When would one decide to use EBS VAC volumes versus NVMe? I think you just answered that, right? EBS, of course, being network attached, is going to have higher latency. NVMe, it's like having an SSD on your laptop. It's instant, or much closer to instant read-write.
Exactly. I would like to add one more statement to that. You need to look at what is your criteria here. So is it a cost optimization or the performance? If you're looking at high performance because you need to deliver a report at certain time to your C-level customers, probably you need something really high performing where you look at NVMe SSD. But if you look at optimizing costs by leveraging and also leveraging wide variety of compute, not just D-type instances, maybe M5X or maybe other instances, then EBS might be a good option for you, because even though there is a little bit of latency, but you get to leverage different types of instances and use EBS as a shuffle data storage for you. So that's one option. And the way you leverage EBS is two types. You can use EBS CSI controller to dynamically create EBS volumes. That is EBS volume per executor. So in the benchmark, we are running 50 executors. That means you will create 50 EBS volumes, one executor, one volume per executor. That's one way. Or you can also create a dedicated EBS volume for each node. So these use cases slightly different from, based on specific your business use case, so that we can help you design what works best for you. But these are the type of instances that you can use. But that's the kind of visualization that we are looking at.
Got it.
Right.
And hey, just as a follow-up question here from David, is one or the other, NVMe versus EBS volumes more tolerant to spot interruptions? You showed that spot managed group. Is
That's a good question.
With the Spark node decommissioning?
Yeah, I think that's a good question. I think that's the reason I said a good question. If you see here, the NVMe SSD is attached to the EC2 instance. If you have 10 executors running on this instance, if there is a spot interruption here, I'm talking about spot here, so you will lose all the executors, and the data that is processed is stored under NVMe SSD. So when the new node comes, driver cleverly spins up all those new executors, right? But it has to, and these executor has to process from the scratch again. They can't process from where it is stopped. But with EBS volume, that is another advantage. With EBS volume, by leveraging Dynamics PVC, there is a feature that a Spark added where you can actually leverage an existing EBS volume. Say, for example, if the spot node is died when you're using EBS volume, when the new executors comes up on a new spot node, they connect to an existing volume so that it can continue where the data was, stopped to process. So you don't have to redo everything. That's one of the biggest use case and useful use case with the EBS volumes when you want to use EBS.
That's really interesting. So if you expect some of your batch processing workloads to take a long time, then maybe it makes sense to use EBS just so you don't lose that progress. But if they're shorter spurts, they can handle that 2-minute node interruption timing that comes from Spot, then maybe you're better off using NVMe. Look, I know we're getting you off track here, but we're getting a lot of great questions in the chat. Do we have an example with Prometheus and Grafana already with the Spark operator? Vara, I know you've got a good answer for this.
Yes, let's talk about the add-ons first. So we talked about the VPC. We looked at the VPC. We looked at the main.tf, which is creating EKS cluster, and also all the node groups. Let's go to, and the next step is add-ons, right? This is where we deploy Spark operator and all the necessary add-ons. So to start with, we have EKS blueprints add-ons we leverage, and you can deploy all the managed add-ons with just enable the add-on. So let me close that. So once you, and then we also have a best practices implemented in a way. So one of the common issues that they get customers is, hey, CodeDNS is throwing in we are getting unknown host exceptions when we are running a large scale workloads, and the CodeDNS, is not scaling. So we added the cluster of proportional autoscaler as a best practice part of the blueprint as well. And moving to,
sorry, go ahead.
So moving to logging, we have FluentBed, which collects all your logs. So currently we are running a Spark job, and all these Spark job logs are collected and written to an S3 bucket and also the CloudWatch. You can choose where you want to, but in this example, we are writing to both CloudWatch and S3 bucket as well. But you can customize that. So that's for logging. For Prometheus, right? So all of these blueprints, one of the main criteria for our blueprints is to give an end-to-end solution that covers logging and monitoring. So we use Prometheus stack pretty much in all of the blueprints. This will help you to actually collect all the metrics, including the Spark metrics, to write to Amazon managed Prometheus. You can even write to your own metric server, external metric server. In this case, we are writing to Amazon managed Prometheus, which is a highly durable, a highly available metric solution. Even if your cluster goes down, the metrics are available. You can still see the Grafana dashboard and to look at your, metrics.
So Prakash, to answer your original question, Absolutely. It seems like most of, if not all of, the examples that we have in data on EKS not only allow you to do that primary use case of running the Spark workload or whatever it might be, but also the ancillary solutions to help support running at scale and in production. Things like having the observability tools, having the cluster proportional autoscaler, the metrics server, logging setup, and of course, you can go in here and click these on and off based on your own needs. Vara, I hate to do this, but I want to get you back on track here. We have about 15 more minutes for a demo. We have a lot of great questions. Guys, keep them coming. We'll make sure we get to them at the end here.
Yeah, sure.
Vara, let's see what happens once we go forward with this Terraform.
Yeah, 100%. So I just want to show you the two key components within so we also created this new data add-ons report to simplify, all the data and ML add-ons. You can find it in this module in the Terraform so you can simply enable Spark operator, whatever you want it to work with. And in this case, it's Spark operator. It deploys Spark operator with a specific configuration. And it also deploys the Unicorn. It's a custom batch scheduler designed for the batch workloads. And especially when you want to do the gang scheduling of your job and optimize your workloads. And this is a great batch scheduler that you want to take a look at it. And Spark S3 server, everyone who's working on a Spark and you really wanted to monitor your workload. So we have seen that before here with the Spark S3 server, how your job, when the job is running and you wanted to see what's happening, with the job in terms of the DAG and everything. So that's part of the Spark S3 server is available as well, and kube cost. So at end of the day, and when you are running a multi-tenant clusters on Kubernetes, and everybody say, hey, how much my data team is spending on the workloads, and you can actually look at kube cost to look at the namespace level costs, and and show it to the right teams and how much you're spending on that. So these are the common add-ons that I wanted to cover, but that's pretty much. And we have other components which part of this, but like Spark team, which is a dedicated team we are creating so that the workloads, when you're running, it will use the dedicated namespace and service account, and also the IAM role back with that service account so that you can have a dedicated policies to run the job. So let's get to the examples, right? This is the main part of this blueprint, right? So when you wanted to run, hey, I deployed everything, I ran install.sh and I got cluster ready, what do I do next? And so you can go and try some of these examples. And the one we have to run is the benchmark. Now, under these examples, we have Karpenter, cluster autoscaler, and benchmark. If you want to try any of these, you can go out, you can go in and run that. And for the benchmark, let me show you something. So benchmark is split into two parts. One is data generation and actually running the benchmark. So data generation, it's a simple, the script that actually generates the amount of data that you wanted to generate in S3 bucket so that you can run the actual benchmark. So in this case, because we are using Spark operator, it's a native way to define the Spark applications in a simple YAML file that you see here, which is Spark operator and Spark application. And I'm also using the namespace that is I created as a part of this blueprint so that I want my workload to run on that namespace. And if you see here, I'm generating the data into my own S3 bucket under specific directory, and the amount of data that I'm generating is 1,000 gigabytes, in this case 1 terabyte, but you can increase how much you want. So in this case, we are not running this data generation now because I already ran and I have the data, but I wanted to show you the spec of how the Spark application looks like. So you can define all the Spark configuration here under Spark conf. And this is the main part you want to get to, the driver and executors, right? So when you wanted to define your Spark job, you need to mount volumes. And the way you mount the volumes are using, so in this case, I'm using NVMe SSD. So I just wanted to show you here. Right. Spark local directory /local1. So as a part of this blueprint, what we are doing is when you create a node group, we're using cluster autoscaler or Karpenter. If that node has NVMe SSD, we are formatting and mounting that node and making it available for you to use under /local1. So which means you can use /local1 as a host path in your data workloads. So all that you need to do is just use /local1, because I can show you where we are doing that bit. And then moving to driver, right? So driver, you wanted to mount this volume with a specific directory. I'm changing a couple of permissions on the driver. And here I'm specifying how many cores I need for my driver. Because it's a data generation tool, I need more cores. So I specified here, but normally you will be doing like 1 core or maybe even 0.5 cores, which is like 200M, 300M, and so on. And then the way you limit, this is like a request and this is a core limit. And then you can also define the memory and request and limits, and which is in this case 10 GB. And the service account, I want to use it so that my IRSA is mapped to that service account. When you run a workload, this job can only access specific IAM policies. And finally, I want to place this driver on this provisioner. So you can even specify more node selectors so that your driver will be placed on specific node. And the same goes to the
a couple of
executive
questions
part.
coming in
Yeah.
chat here. From Sunil, will the local one mount path be used for shuffle as well?
That's correct. So mainly for shuffle in this case, we are using /local1 for shuffle. But I can show a quick example of here, how that looks. This is so.
And hey, Bara, this actually goes hand in hand with another question here from Andrew Poloni. With is there any advantage to integrating your EKS deployment to placement groups to take advantage of the networking speeds? Of course, placement groups can be spread for more high availability or clustered for the networking advantages. And of course, we know that with the Spark shuffling, where that local file system is being used, there's definitely considerations on how that spread of the data happens between the nodes where the Spark workloads are running. So would you recommend using placement groups?
Yes, if you wanted to have a better performance and you can leverage placement group, but you really have to, sometimes I say don't overkill. If you have a job that is performing based on your requirements using like maybe 30 minutes, but in cases where you want to further improve it, yes, placement group is another thing that you want to think about it. And this is especially used for the machine learning workloads when you want to do distributed training and across multiple nodes using PyTorch or a TensorFlow. So yes, placement groups, and if you come down to the machine learning distributed training, you can even look at EFA, which is Elastic Fabric Adapter, to have a high performance distributed training as well. So I don't want to divert to the machine learning, but yes, those are definitely the options that you can take a look at that one. So let's look at the benchmark. So going back to the question, yes, /local1 is a shuffle data mainly. The actual data is stored in S3 bucket. We pull the data into /local1. And once the shuffling is complete, once the data processing is complete, data will be removed from this, and then finally you write the data back to an S3. So that's the volume here. So let's look at how to run the actual benchmark. So once you run this data gathering, data creation, so you will create the data set under EMR Spark benchmark. So, and the next step is you point to this bucket and run the actual benchmark results, so which is this job. So let's take a look at the difference. Is not much we're using. You can leverage our public ECR image for the benchmark. In this case, I will be writing the results back to, because it is the benchmark itself, what it is doing, it is reading that data warehousing data, simulates the data, e-commerce data, reading all the data, and runs a couple of joins and maybe aggregations and filtering the data, and finally write the data back to results. So, and that will give you how long it took to process this amount of data based on the type of compute and storage that you use, so that you can further look at adding placement groups, changing the storage type, and changing the compute type to further improve the performance so that you can run new workloads. So that's this job. It's pretty much same as that. We will be using same /local1. If you see everywhere we use /local1 because that's mounted when you're using D-type instances. Yeah, so to run the job, all that you will be doing here. So let's go to the directory. In this case, benchmark. So once you have the cluster up and running, and once you have generated the data, and then you come to this location, which is benchmark. And then we have two scripts here, YAML files in this case. The way you deploy Spark operator, which is nice in this case, you just use kubectl command and apply. And kubectl benchmark that. So here I'm running kubectl apply, but in production, you might be using schedulers like Airflow or Argo Workflow. Could be anything. So if I run that, because my job is already running, it says unchanged. I started this job because it's a long running job. This benchmark can run for 2 to 3 hours. It depends upon the size of the data. So let's go back to that job. So the first thing to start with, Spark Team A. This is the namespace we are running the workload. So the way I just filtered out all my parts that are running Spark Team A. But you can also see Spark History Server. If you want to look at Spark History Server, it is available under this. You can just choose Spark History Server. And let's look at Spark Operator. And this is the Spark Operator, the operator which is running that we deployed as a part of that. It also uses mutating admission webhook, which is mainly used for mounting your volumes and so on. And that's a Spark operator. And then you want to look at Unicorn. So all of these namespaces that you see here, and all the data, all the parts related to that namespace are stored in this Kubernetes stack. And we have Karpenter and the kubecast, pretty much everything.
Vara, just chiming in here. I know you also wanted to talk about EMR and looking at the namespaces. That reminds me that EMR is part of this. We have about 4 or 5 minutes here for the demo. Do you want to quickly talk about the EMR approach to running this? And in fact, we also got a question in chat earlier about learning, some of the differences between EMR and EKS versus Amazon EMR. And of course, we'd all want to know how to run Spark on EMR as opposed to the Spark operator approach that you just showed us as well.
Sure. I can take that first, EMR versus EMR and EKS bar if you want to take the time to pull some things up. So with EMR on EKS, if you have existing EKS infrastructure, you can start to consolidate those EMR applications on that infrastructure. So that's that standardization piece I was talking about earlier. The other thing is cluster startup time. So if you are running EMR and EC2, starting a new job, oftentimes you have to start up a new cluster. Not something if you already have that EKS cluster running, you can just deploy the application there. Man, those are the big ones. I feel like I'm blanking on a third. Var,
Alex, I would maybe add one to your second one of, with EMR and EKS, you can even use Karpenter to set up provisioners and just say, hey, use all of these different types of nodes and you figure it out. You do the heavy lifting and you just tell it, hey, run this job for me. And it'll take care of spinning up that compute specifically for your set of workloads.
Exactly right. So I would like to add one point here. So Spark Operator, it's an open source solution. So if you, in the organization, you have a team who can manage and fix issues and work with that, and you have to work with the Spark Operator. But with EMR and EKS, there is no operator involved here, which is using EMR and EKS API to submit the job. It uses Spark Submit. So there is no management of Spark operator. You can simply use EMR and EKS API to submit the jobs. That is one easy thing. And you also get support from EMR team if you get stuck anywhere. And pretty much everything that you can do, with open source, you can do with a Karpenter, with EMR and EKS as well. So the way we have a dedicated blueprint for that, in this case, EMR and EKS Karpenter will go through the details of the best practices of how you can actually deploy that, which is pretty much same as what we have seen with Spark operator like VPCs, main.tf. But let's look at the Karpenter. That's the area that we haven't covered, right? So I would highly recommend when you're looking at, bursty workloads where you wanted to optimize costs, try looking at the Karpenter rather than Cluster Autoscaler, because that'll give you a lot of flexibility. In this case, I created multiple provisioners: compute, graviton, and memory. So if you look at this, the Karpenter provisioner, if you see, I'm using a single AZ. Most of the data workloads are a single AZ for high performance. So you don't want to really run your workloads across two AZs. That slows down your performance and also the cost of data transfer as well. So that's why it's a single AZ. And this is the beauty of the Karpenter. You can choose spot and on demand, and it'll try to look for the instance where the spot is available. If not, it falls back to on demand, right? And in this case, I'm using C5D 9x large. It's only one instance specified, but it's a list. You can choose C5D X large to 24x large, or mix up all the instances for running your workload. And the way you use a specific provisioner is again using the labels and taints. And there are no taints here, but you can add taints, and then you can tolerate add tolerations to your jobs and also labels to run the job, right? And this is the node template. This is the bit, and I wanted to show you. The node templates is similar to the launch templates. Like when you were using cluster autoscaler, the launch templates will create a node for you. In this case, node templates are helpful for you to modify any node characteristics in this case. And I want to create GP3 volume, a specific GP3 volume with 100 GB, because by default, Karpenter creates 20 GB, but I need more volume for the root. So I use 100 GB here. That's where you define what you want there. And this is the user data. So I want to get to the point, like I mentioned, the way this is a little bit of a script. Simply, it looks for if there are any NVMe disks available on the node. So if you're using mix-up instances, say, for example, C5X large or D-type instances, and this user data is all about finding, does this instance has any NVMe SSD? If it does, and it goes and sometimes some instances have multiple NVMe SSD disks, right, within the same instance. So to make it easier, what we are doing, we are formatting and mounting those disks, and also creating a RAID 0, so which will give you a single directory. That's where the /local1 comes into the picture. The /local1 is going to be your host path when you wanted to run your workloads. So which means every time Karpenter spins up a node for you, it also formats and mounts your NVMe and make it available for you to use it in your workloads. All that the DevOps and the teams will let data teams know that you can use this /local1 path for your shuffle data, temporary data, wherever you want. So that's the Karpenter provisioner.
I've got to say, Vara, this is exactly why I highly recommend folks that are watching if you're looking to do AI/ML workloads, Spark on EKS, start with data on EKS, because it's things exactly like what Vara walked through that are complicated, small gotchas that our team, folks like Vara, have gone through, figured out the solutions for, and published them on the repository. That's really why data on EKS helps you get started so much more quickly, because I can't imagine having to figure out how to set up a RAID of NVMe SSDs on my own for Spark workloads. Someone's done that for me. Awesome. So it looks like you've executed the task, by the way, and we have just
I thought I wanted to save some time. I wanted to save some time. So there's a couple of examples here, and I wanted to show you how you can actually use it, how this is different from open source, right? So in this case, the example I just executed, we can take a look at the parts in a minute. It's under Karpenter Compute Provisioner Examples NVMe SSD. So if you go to Examples under EKS Karpenter, NVMe SSD, a Karpenter Provisioner, if you see there's three, I want to walk through it quickly. So we are using pod templates. With Spark, with EMR and EKS, you can leverage pod templates. You can create, pod templates are useful when you wanted to mount the specific volumes that can be PVCs or using host path. And then you can use node selectors and taints and tolerations applied to pod template. And same for the executor. I'm using /local1. Here, I'm using my namespace and also node selectors and the containers where it should be mounted on data one. So to run this job, all that with the EMR and EKS, you only have to run this command, which is AWS EMR containers start job run with a spec. So to simplify this, I created a shell script, which basically creates a test data for you and then extracts the virtual cluster ID and then run the job for you. So when you look at it, so that's the job I just ran. This is what this is doing is I'm using a New York taxi data. It's an open data set to read this data from S3 bucket and then do a bit of a processing. That's the PySpark script here. And then repartitioning the data and writing back to S3. Just to show an example, there's nothing magical here, but this is just to show an example how this works. So I just triggered that. As you see, it's a shell script I triggered and I entered my region and the job has started. So let's take a look at where the job is running, right? And this is under the namespace. Let's go back to the job that we executed with the driver template. So I'm using EMR data team A namespace. This is where the job triggered. So if you want to take a look at the jobs, you can run kubectl on get pods on this EMR data team A. We can even take a look at so in this case, yep. So I filtered on EMR data team A. You see that the first one is a job. So what EMR does, EMR and EKS does, it creates a job object, job pod, which actually controls the whole execution thing. Unlike a Spark operator creates a driver pod first, and then the executor gets created. But in this case, the job pod here, and it actually triggered the executor driver pod, but it's taking some time because it needs to spin up. It needs to create a node because I'm using Karpenter here. You see that the node is bound now, 6924. If I go to the nodes, there is 82 seconds, and I got a new node 6924, which is using C5D9X large. Because I only specified one instance, but you can choose different instances. So
sounds good.
As you know,
yeah. Farah, and I hate to interrupt you here, but we're well over time here. But if I had to summarize what we're looking at here with EMR on EKS running the Spark workloads, we're seeing a more managed style experience. There's lower overhead. Of course, with the Spark operator, you're managing additional components in the cluster. It's a more open source centric experience, but of course, more overhead. With the EMR on EKS approach, you're getting that kind of more managed experience. Really, the core value add of AWS services as a whole is us handling some of that undifferentiated heavy lift for you. And that's really where solutions like Karpenter for compute provisioning and then the EMR on EKS API call, rather than working with YAML, working with the operator, makes that Spark execution a bit easier. I'm also going to drop a message in chat here showcasing the benchmarking data of running EMR on EKS for Spark workloads, which shows a noticeable improvement. I see you pulling up the Grafana dashboard here, Vara. So as we kind of see that data, I just wanted to tell folks at home, thank you for tuning in and watching this. If you have any more questions, I apologize we couldn't get through everything that we wanted to today, but be sure to check out the repo, Data on EKS. I'll drop a link in the chat here in a second. And if you have any further questions for this demo, or you want the slides or something like that, reach out to Vara Bantu or Alex Lines on LinkedIn. Is LinkedIn good for both of you? They'll both be available there if you want to ask any questions. Here's that link to Data on EKS. Vara, Alex, any last minute thoughts you want to share?
No, just there's one thing. If you're thinking about migrating your data workloads onto Kubernetes on Amazon EKS, try to reach out to your solution architects or try to reach out to the Data on EKS team and see how we can help you to actually build that and help you do the POC and even productionizing your workloads.
Yep, plus one to that. There's a lot of knowledge baked into those blueprints and a lot of folks here to help. So don't hesitate to get in contact with us.
Absolutely. Thank you so much, Alex and Vara, for joining us on Containers from the Couch. This was a super insightful session. Thanks for the folks watching at home. Be sure to subscribe and follow Containers from the Couch to see more episodes like this in the future. We'll see you next time.
Right. Thank you.